So Unit 9 brings us into probability. So with probability, we are attempting to assign a number to the likeliness that an event is going to occur. I mean, that's just fancy for something you hear every day on the news. The weather. There's a 30% chance of rain today. There's a 100% chance of snow showers. Just like you guys when you're looking forward to a snow day. Yeah, but they said it's going to snow 100%. So we have some basic terminology first that we have to learn. An experiment. So when we are studying probability, we're going to run some experiment. And it's a process that occurs with well-defined outcomes. So in other words, we set up the experiment because we want to study something. So that's the well-defined outcome. We want to see that if we do X, will event Y occur? An outcome is a result from a single trial of an experiment. So to do an experiment, we must do a lot of outcomes, which are called events, a collection of one or more outcomes. And then the sample space is a collection of all the possible outcomes of the experiment. So the probability of an event E occurring is given by the ratio, and here, this is fancy terminology for the probability of an event is defined by a fraction, where n of E is the number of outcomes that fall into event E. So in other words, I call these successes. This is what we're looking for. We're looking for something to happen. Those are the successes, and n of S is the number of outcomes in the sample space. I called this the total. So all probability has to lie between 0 and 100% inclusive. In other words, 0% means it's not happening. 100% definitely going to happen. Right? 100%. What's the probability the sun will rise tomorrow? 100%. Yay. What's the probability that a cat's going to bark? 0%. Cats meow. Anyway, example 1. A fair coin is flipped 3 times and the result is noted each time. The sample space consists of ordered triplets, which represent a head and a toss on the first toss, a head on the second toss, a tail on the third toss. All right. Let's look at the difference between sample spaces. Move this down here because I'm going to need some room. You're most likely familiar with a tree diagram. So a tree diagram would look like this. You're going to flip a coin 3 times. So the first time you flip that coin, it could land on a head, or it could land on a tail. You get to flip that coin again because it said 3 times. So, branching off, you would have this. Given the fact that your first time was a head, your second flip could be a head. Or, given the first time you flipped it was a head, it could land as a tail. And likewise, that can happen down below. Now, you still have one more time to flip. So I could branch off of each one of these. And each time, it could be a head or a tail. So it could be head, tails, head, tails. That's it. So if we were to come back up here and we look at this probability again, Remember that the number of outcomes that fall into the sample space. So the total number of outcomes, if I flipped a coin 3 times, is 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 total outcomes. Because that was the last branch of our tree. Now, if I did order triplets, some people like sample spaces. Sample spaces as ordered triplets in this way, it's a little more confusing. You have to be very organized. So you could say, all right, I could flip the coin 3 times and it could all be heads. I could flip them and it could go heads, heads, tails. And then they usually put these in parentheses, but I'm going to not put them in parentheses because I got too much to do here. God, I need total outcomes. So it could go heads, and then I could get tails, tails. All right, what else could I do? I could go heads, tails, and then heads. I could go heads, tails, tails. No, I got that one there. Darn, this is why I don't like sample spaces. They take too long. And you have to keep very organized. All right, I could start with a tail, and then go to a tail, and then go to a tail. I could start with a tail, then go to a tail, then go to a head. I could start with a tail and then go to a head and then go to a head. Or I could start with, what's the only one I'm missing? Starting with a tail, going to a head, and then ending with a tail. Boom. 8, 8. I match. All right. Now let's start doing some probability. What's the probability that I got all heads? Well, I want the number of times I got heads over the number of sample space, total outcomes there were. So how many times did I get all heads? Just once out of the 8 possible outcomes. Right here, and obviously right here. All right, how many times did I get exactly 2 heads? Well, I'm looking for the number of times I got 2 heads over the number of my total outcomes. Well, my total outcomes, once again, we know are 8. So how many times did I get 2 heads? Exactly 2 heads. Well, right here I got 3 heads. That's not right. Heads, heads, tails. Okay, that's 1 time. Heads, tails, heads. That's the 2nd time. Heads, tails, tails. Nope. Tails, heads, heads. That's the 3rd time. Tails, heads, tails. Nope. Tails, tails, heads. Tails, tails, tails. So according to me, I got a head twice, 3 times. Let's check over here. That doesn't count. That counts. That doesn't count. That counts. That doesn't count. That doesn't count. That counts. All right, so it works 3 times. Now, what's the probability I got all heads or all tails? So I can win on either way. So that's the number of all heads or all tails over the number of outcomes. Well, the number of outcomes we know is 8. And how many times did I have all heads? Once. How many times did I have all tails? Once. So 1 time plus I could win on that time means 2 out of 8, which reduces down to 1/4. Sometimes we have to quantify chance by using observations that have been made in the real world. In this case, we're talking about empirical probability. Well, empirical probability just means an observation. You're not controlling it, you're observing. So really, this was empirical also. You were flipping a coin and observing what came out. So here we observed the answers to a survey. And a survey was done by a marketing company to determine which of the 3 sodas people preferred in a blind taste test. Here are the results. So once again, first thing I notice is the total, 53. So that would be the number of outcomes. We could have had 53 possible different outcomes. Well, you're like, but they're only tasting 3 different sodas. But we talked to 53 people. And then our events are basically based on soda A, B, or C. So find the empirical probability that a person selected at random from this group would prefer soda B. So empirical probability is just fancy for I observed people. I observed 53 people. And how many people picked soda B? 24. Now express your answer as a fraction or a decimal. Well, that's kind of easy. I just do 24 divided by 53. So that's 0.45. Cinch. Find the empirical probability. Once again, that just means part over total. Number of successes over number of outcomes. That a person selected at random from this group would not prefer soda A. Well, if you don't prefer soda A, you must prefer soda B or C. Oh, okay. So 24 people liked soda B and 11 people liked soda C. So that brings me to 35 people who didn't drink soda, who preferred, sorry, let me get that right. That means 35 people did not pick soda A. And we know that we're 53 people as my outcome. And again, divide that out, and I could express it as a decimal. And basically, you hear marketing, they express it as decimals. Because if Pepsi were to say that 24 out of 53 people preferred Pepsi, half of you on the TV would go, what? But if you said 45% of the people preferred Pepsi, you're like, wow, that's a lot amount. How about 66% preferred Pepsi? Now they're selling it to you.